So let's look at this problem one more time to try finding the radius of the circumcircle of a quadrilateral. This formula is well known. It's due to Parameshvaran, Namboothiri, an Indian astronomer from 1500 or so. And in any case, I'm going to show a simple derivation of this formula. So I'm going to start with a triangle. And this will be useful. So we have circumscribed a triangle. So the way you circumscribe is you find you draw the perpendiculars to the sides. Let's draw two sides. So two lines to meet at a point. Let's call it O. And then so if you look at these two triangles, they are congruent because basically this is the two sides are equal. This is a by 2, and this is common. So the three sides are equal. So they are congruent. These angles are 90. So these two angles are equal. So let me call it Z. And now if you join here also, again, you can see that this side is common, this side is common, b by 2, b by 2. The one angle is so two sides and an included angle are equal. So these two triangles are common. So if this is also R, so that means, and then this is R. This, if you draw a perpendicular, so perpendicular bisectors meet, and that's the center of the outer circle. So now another property is this whole angle is A. So if I call this angle to be X, so then this will be X. And if I call the remaining part to be Y, this will be Y. And this whole angle is B. So this inside angle is B minus X. This inside angle is C minus Y. So from this triangle OBC, if you look at the angles, you get 2Z plus B minus X plus C minus Y. This is three angles equal to pi. So you get 2Z plus B plus C minus X plus Y equal to pi. But look at the diagram. X plus Y is A. X plus Y is A. So you get 2Z equal to pi plus A minus B plus C. So that's 2A because pi minus B plus C is A. So this is a classic result. The angle projected at the center is twice the angle at the circle. So A projects 2A here, and these two angles are equal. So Z is A, so Z equal to A. And so from here we get some useful identities. You see that A by 2 divided by R is a sine of Z. Z is A, so you get this property. A by 2 divided by R is sine Z. C is A. And consequently, you get A equal to 2R sine A, or R equal to A equal to 2R sine A, or sine A equal to, rather, either way, sine A equal to A over 2R. So we'll use this relation. This is just a quick review. And similarly, an area of a triangle is, if you have a triangle, so notice that the way I have drawn this triangle, H is C sine A, So area is half BH is half BC sine A. But we just had it in the earlier slide. A is sine A is A by 2. So this is a useful relation that I'm going to use again and again for the quadrilateral. So that's all we need from the triangle thing. So let me go to a quadrilateral. And in fact, these are special quadrilaterals because you can inscribe a circle or circumscribe a circle. So they are called cyclic quadrilaterals. In other words, there is a circle which touches all the four corners. So if that is the case, if you join this line to the center, then you notice that if you take this triangle, this angle will be 2C, and this angle will be 2A, if that's possible, because from the same property that I just mentioned. If you consider this triangle, let's say ABCD. If you consider the triangle ABD, then this A projects here at the center 2A, C projects 2C, but 2A plus 2C is 360, or A plus C is pi. So this is necessary and sufficient. So this is clearly necessary. And I'm going to show that this is also actually sufficient while I do the construction. So this is where we start with. So this is the condition for a cyclic quadrilateral. So if you can circumscribe a circle, then the opposite angle. So if A plus C adds up to 180, then B plus D also adds up to 180, because the AB plus C, A plus B plus C plus D is 360. There being four corners. So let me derive the area of the quadrilateral quickly. This special quadrilateral. So I'm going to make use of this property twice. So the way I'm going to do is, so let me redraw this quadrilateral one more time here. So area is the two areas, A1 plus A2. So let me call this diagonal to be P. So then you have two triangles. So the area of this triangle is ABP divided by the radius 4R, using this formula. So the key is that wherever is the origin, the radius, it must be go through these two. If it goes through these three, the same circle is circumscribing these two triangles with the same center and same radius. So for this triangle, the two sides are ABP, and for this triangle, it is CDP. So the total area is AB plus CD multiplied by P. So the question is, what is P? And in the previous derivation, I used Ptolemy's result, but we can do it without that. That's what I figured out. So for that, I'm going to look at the property, take advantage that P shares a common side to these two triangles. So notice that P squared, from symbol, we have two equations for it, because it's going to be from the diagram A squared plus B squared minus 2AB cos A. But also from this triangle, it is C squared plus D squared minus 2CD cos C. But remember, C is pi minus A. So cos C is minus cos A. This minus will become plus. And I'm going to equate these two relations. So you get A squared plus B squared minus 2AB cos A equal to c squared plus d squared plus 2cd cos A. So we can solve for cos A. Cos A is 2 multiplied by AB plus CD equal to A squared plus B squared minus C squared plus D squared. So cos A becomes A squared plus B squared minus C squared minus D squared divided by 2AB plus CD. And so that's one, that this is a useful identity for quadrilateral, for the for a cyclic quadrilaterals. And now I'm going to use this and substitute it into one of these relations. So p squared, because if I can get that, ultimately I can substitute for p here. So p squared is a squared plus b squared minus 2ab cos A. So that's going to be a squared plus b squared Yeah, so this I'm going to substitute for cos A. So 2 multiplied by AB plus CD. So if I here 2 cancels, and if I cross multiply, I get A squared plus B squared multiplied by AB plus CD minus AB, A squared plus B squared minus C squared minus D squared. The whole thing divided by AB plus CD. So notice that AB multiplied by A squared B squared is common, and it cancels out. So this cancels with this. So we get P squared, which is A squared plus B squared multiplied by CD plus C squared plus D squared multiplied by AB divided by AB plus CD. So this is for P squared. And I'm going to, so let's look at the numerator of this P squared. I think we can simplify that. So A squared, just the numerator, A squared plus B squared, I'm going to expand that. So that's A squared CD plus B squared CD plus C squared AB plus B squared AB. So this is equal to, if you look at these two sides, AC is common. So then you have AD plus BC. And here, I guess BD. Then you have BC plus AD. So you can write this as AC plus BD multiplied by AD plus BC. So let me substitute that into the numerator. This is just the numerator. So P squared turns out to be AC plus BD multiplied by AD plus BC over AB plus CD. So I'm going to take that and put this into this expression. Okay, here I guess I missed there's a 4R, ABC by 4R, so there's also an R here. So we get area, which is 1 over 4R multiplied by AB plus CD multiplied by P. So P is the square root of this. So if you substitute, you can see that you'll get this to be, you get one factor from here because the P squared is this. So P is, of course, the square root of this. So square root of AB plus CD cancels with this. So essentially you get AB plus CD multiplied by AC plus BD multiplied by EAD plus BC. This is exactly the same formula we would get if we use the Ptolemy's relation also. But being a cyclic polynomial, I just exploited the fact that A plus C is 180. Now, we can also use this to use this P formula, or rather the cos A formula, to find the area of the triangle another way. So area of the quadrilateral, I meant. So area of the quadrilateral is once again these two areas. So this area is another formula is going back to the triangle. Again, so for any triangle, area is two sides and the angle from the BC and the included angle, sine A. So for this triangle, it will be AB sine A. For this will be CD sine C. So area is half AB sine A plus half AB sine A plus half CD sine C. But sine C is the same as sine A. So you get this is half of AB plus CD sine A. You want to eliminate sine A, so I'm going to do A squared. That's 1/4 AB plus CD squared sine squared A, which is 1 minus cos squared A. And for cos A, I am going to substitute from here, from number 2. So this will turn out to be 1/4 AB plus CD 1 minus A squared plus B squared minus C squared minus D squared, the whole squared over 4 AB plus CD, the whole squared. All right, so I'm going to notice that when I bring this over here, this will cancel. AB plus CD squared will cancel, giving us 160. Then 2 AB plus CD squared minus A squared plus B squared minus C squared minus D squared, the whole square. So this is like x squared minus y squared. So you're going to get x plus y multiplied by x minus y. So this will be, x is this, 2ab plus 2cd plus this, plus a squared plus b squared minus c squared minus d squared multiplied by x minus y. 2ab plus 2cd minus this, minus a squared minus b squared plus c squared plus d squared. So this is 1 over 16. Notice a squared plus b squared plus 2ab. So that is a plus b the whole squared. Then you have c squared plus d squared minus 2cd. If you pull out the minus sign, so that is c minus d the whole squared. This multiplied by, same thing here, c plus d the whole squared. I'm going to write it the other way, c plus d the whole squared minus a minus b the whole squared. So we can do this one more time inside. So that would be, so you get a squared is 1 over 16. Notice that this will give us a plus two terms. This is a plus b plus c minus d multiplied by a plus b minus c plus d multiplied by here a plus c plus d minus b, and the last term is minus a plus b, so that will be b plus c plus d minus a. But as we have noticed before, this is actually s minus a multiplied by 2, because s, if you take s to be half half the perimeter, and then s minus a is a plus b plus c minus d minus 2a. So that's going to be a plus b, or b plus c plus d minus a by 2. So 2 times this is b plus c plus d minus a, etc. So this is s minus d. This is 2 times s minus a. This is 2 times s minus c. This is 2 times s minus b. So 2 4 times that 16 cancels, and you get this simple formula, s minus a multiplied by s minus b, s minus c, s minus d. I believe this is due to Brahmagupta. So for the area of the cyclic quadrilateral, it just depends on only the 4 sides. All right, so we have, I'm going to call, let me call this to be 5. We have formula for A one way, and we also have we have formula for A other way. So I'm simply going to equate, and that is Parameshvaran's formula. So A turns out to be just 1 by 4, or previously AB plus CD, AC plus BD multiplied by AD plus BC. But this is also equal to S minus C multiplied by S minus B. So from here we can solve for R. All right, so this is the formula we had for Parameshvaran's formula for the radius of the circumcircle of a quadrilateral. Of course, the quadrilateral is cyclic. I believe this is around 1500 or somewhere around there. So Parameshvara is from the bottom part of India, a place called, a state called Kerala. Now I want to summarize this with maybe just one observation on a general quadrilateral. If you take a general quadrilateral, A, B, C, D, so notice that is AB, what all you need to complete a quadrilateral. So for a general quadrilateral, so it so happens that the four sides are not enough. Of course, you need because you can see here, if you are given, you take two sides, you can the if you specify this angle, then this point becomes, though this becomes the triangle ABD becomes specified with the two sides, and we call this to be P. And then basically you have these 2 points, and there's only one way to go. So I'm going to generally show that in addition to ABCD, you also need an angle A. So you can see it from here. So again, the same relation, P squared from here will be A squared plus D squared minus 2AD cos A. And from here it is, if this angle is C, B squared plus C squared minus 2BC cos C. So if ABCD, given ABCD and A, then you can figure out C. You can figure out this angle. And then the quadrilateral is completely fixed, because all the other angles. So you have cos A is given, then cos C is, you can solve from here. So that gets a C. And as I said, you can also see it geometrically. Once A is fixed, these 2 points are there. Then essentially you have the three sides of the other triangle, and there is only one way to fit it in. And this is the way you get, once A is given, you can find out to C. So you have, and then B plus D is remaining A plus C. And the B also we can figure out by, this gives P, and then you have Q. Essentially you can also find, because and then you can find the other two sides. Whereas for a cyclic quadrilateral, once even the angle is not necessary, the sides are enough, because cos C is the same as, if ABCD is cyclic, then C is pi minus A. So the sufficiency was just before that, the sufficiency for cyclic quadrilateral that A plus C equal to pi is enough is just this proof. Given that the fact that I can complete the circumcircle, and in fact the radius is here. So C is pi minus A, so cos C is minus cos A. So you get cos A, we had this formula before, is A squared plus B squared minus B squared minus C squared over 2 AD plus BC. And so another condition is that if this quantity is less than 1, then using the given ABCD, less than or equal to 1, then using the given ABCD, there is an angle A which is realizable, and you can draw A, that gives you C. And if you use these two triangles, similarly you can find out a B also uniquely. And that's all. So so given ABCD, what values of ABCD will make a cyclic quadrilateral? I believe this is the condition. This quantity and the needs to be less than 1. So I'm going to stop here. The whole goal was to sort of derive the Parameshvaran's formula without going through Ptolemy and all that stuff. Thank you.